Hello. Today we're going to talk about quantum physics and attempt to show through a simple thought experiment what makes it so different from anything that we're used to. This is a variation of an argument that I originally encountered in a video lecture by Sidney Coleman called Quantum Mechanics in Your Face, which is one of the very best lectures that I've ever seen, so I'll make sure I post a link to it in the description. Anyway, it's based on an argument originally by John Bell and later refined by Greenberger, Horn, Zeilinger, and David Mermin. In this case, we'll present it as a variation on a game of shells. Say we have 6 shells arranged in 3 columns. Let's call the top row T and the bottom row B. Under each of the shells, there may or may not be a P. To play the game, I can uncover exactly one shell in each of the 3 columns, either the top one or the bottom one, but not both. As I play the game over and over again, I notice a pattern emerge. Whenever I open one top shell and 2 bottom shells, I observe that the total number of P's is even. Sometimes I count 2 P's, sometimes I count no P's, but I never see 1 or 3 P's. While curious, there's nothing too strange about that. There are ways that the game master could have set up the game ahead of time to achieve that result. For example, he may have put no P's under any shells. Then, no matter what, we would always count 0 P's. Or else he may have put 2 P's in the top row and 1 in the bottom row. Then, depending on which top shell and which bottom shells we chose, we would either count 0 or 2 P's. But one thing you'll notice about both of these possible configurations is that the total number of P's in the top row is even. In fact, we can show that this is always the case for any possible configuration. If we uncover the top shell on the first column and the bottom shells on the second and third columns, we'll count an even number of P's. Mathematically, we can write this condition as T1 plus B2 plus B3 is an even number. But the same applies if we uncover the top shell on the middle column, meaning B1 plus T2 plus B3 is even, and the final condition is B1 plus B2 plus T3 is even. Now we just add these equations together and group terms. We can then solve for the sum T1 plus T2 plus T3. Look at the right-hand side of this equation for a moment. We have an even number minus another even number. That means T1 plus T2 plus T3 must also be an even number. You should be totally convinced of this result before you go on. You may want to pause the video for a moment and review the argument to make sure everything makes sense. Well, the amazing thing about quantum mechanics is that it lets us set up such an experiment where we will always count an odd number of P's in the top row. So not only does quantum physics break the rules of classical physics, it seems to break the very rules of logic. After all, we didn't use any classical physics in our arguments here. We just used some basic reasoning about even and odd numbers. This is the essence of quantum weirdness in a literal nutshell, and it has profound implications for the very nature of reality. We'll explore those implications in a future video. But before we close this video, I want to close one possible loophole that you may have spotted. You may suspect that the game master is cheating. Say, for example, that we start off with no P's under any shell. After we open the left shell, the game master reacts to our decision. If we choose the bottom shell, he does nothing, ensuring that uncovering 2 bottom shells and 1 top shell will always give an even number. And because we've already uncovered 1 bottom shell, there's no way we would ever know that there isn't an odd total in the top shells. If we choose the top shell, he quickly sneaks a P into the top middle shell. So now, if we do open all 3 top shells, we'll count 1 P, an odd number, and if we open the other 2 bottom shells, we'll count no P's, an even number. But we can actually close this loophole by moving the shells far enough away from each other and uncovering the shells virtually instantaneously, or at least quickly enough that there's no time for the game master to respond to our decisions and manipulate any other shells. In physics terms, we would say that these games are now space-like separated, meaning that for the outcome of any one game to affect any other game would require a signal to travel faster than the speed of light. In a separate video, which I'll link in the description, I explain why that would cause major problems for modern physics. So, in this video, all I've done is claim that it's possible to set up a quantum experiment that exhibits this strange behavior. But I haven't told you how to set that experiment up. That will be the subject of the next video in the series.